Welcome back. This is another type of descriptors for the boundaries, which is called the signatures. First of all, let's start with the definition of a signature. The signature is just a one-dimensional function that represents the boundary. That is, instead of representing the boundary in two dimensions, which is just the shape of the boundary in the image, we just reduce that to one dimension, right? So we get a one-dimensional function, and there is several ways to get that descriptors or that function. So one way is by let me just first show you an example before talking about this method. For example, let's say that I have a square. So what I do to get one way to get the signatures is the line, or is the distance of the line that starts from the centroid of my shape to the boundary point, right? And of course this should be a function of angle. So this is my line. In that case, let's say that the amplitude here is A, right? So what I do is that I plot a one-dimensional function, and this is my signature, and this would depend upon the angles. This is the angle, and the first point here is A. So what I do is that I rotate that line by 1 degree, and then I plot again the amplitude. And if I do that on the entire shape, of course, I would get something like that. So you have here two peaks, 1, 2, 3, and 4. 1, 2, 3, and 4. And then I go back to my minimum value. And of course, these peaks, these 4 peaks, represent the position when this line reaches this position, this position, this position, and again this position. Therefore, I have 4 peaks, right? So this is a way to get the signature of a given shape. So this now represents a boundary. This is a boundary descriptor. And of course, it is represented in the form of a feature vector. So I have to resample that. I have to take samples from that function and then create my feature vector, right? Now what I want to do is to talk about some normalizations. If the position of this rectangle changes, then obviously this signature would be the same, but if I have a change in rotation or a change in scale, then I would get a mistake. So first of all, I will talk about normalization against rotation, which is kind of similar to the normalization against rotation for the case of the chain code. So what we do is that we just start from the point that is farthest from the centroid. So in that case, it's this point, or the point that is nearest from the centroid, which is this point, right? And then we just take this point as a starting point. So for example, in this case, if I would start by the point that is farthest from the centroid, this is the new descriptor that I would get, or rather the new signature, right? So this is my signature, and this is the maximum value. It's at theta equal to 0. And of course, as I just said, we can start from the minimum value. And one drawback of this method is that it's sensitive to noise, because this minimum and maximum value can actually be just a noise, right? So there is an alternative for that, which uses something called the eigenaxis. It's more robust, but it's computationally more expensive, right? So I'll not talk about that here. What I will talk about is how to get a normalization now against changes in scale. Well, say that I have another rectangle but is 2 times bigger than this one, a rectangle like this one. So obviously what happens is that the distance from here to here increases by 2. The same thing is true here, right? This means that this amplitude would be 2 times larger, right? So it would be something like that. So A, the minimum value would be 2A, right? And then of course say that this value here is B, then the maximum value would be 2B, right? And this would be my signature. So this is a signature that is associated with this bigger shape. Well, how to deal with that? So to deal with that, we need to bring this signature to the range 0, 1. And the way to do this is, again, by taking the minimum value and the maximum value and mapping all my samples in my signature into that range. So this is what I should do. I should create a function like this one. This is a mapping function. So this is the new sample that is of course normalized against scale, and this here is the old sample. So what I do is that I figure out the minimum and maximum value. This is the minimum value and this is the maximum value. So in that case it would be this value here. The minimum value is A and the maximum value here is B for that old sample. And what I need to do is to create a mapping function that would map all my samples in the range 0, 1, right? So I should get a linear function like this one. So in the next, for any shape that has a different scale, no matter how scale it is, no matter its scale, I would always get a value or samples that are in this range, 0 and 1, and this thanks to this mapping function. So this is a way to get a normalization against scale, but as I said earlier, we have this problem of noisy shapes, that is, this minimum and maximum value can be affected by the noise, so we can get a significant change in the maximum value, for example, and if this happens, then this mapping function would also change, right, because it depends upon this maximum value. So a robust way to do that, or to get a normalization against the scale, is to use the variance, right? So the variance is proportionally dependent upon scale. That is, when scale changes, then the variance, or rather when scale increases, then the variance increases as well, and when the scale decreases, then this variance decreases as well. So because this proportionality that I have between the variance and scale, one way to get a normalization against scale is to divide each sample in my signature by the variance. And this is a way to get a more robust invariance against changes in scale. So I want to talk now about another way to get the signatures. So this was the first way, and of course I said that we need to plot the distance from the center to the boundary and get a one-dimensional function that depends upon theta. So theta here is equal to 360 degrees. Well, what if I have some other shape like this one? Say I have, for example, a segment for the number 3. And say that this is the centroid. So what I would do is that I would plot this distance and then this distance and then this distance, and notice here that here I have, this is the first boundary. Normally this line crosses this point of the boundary, and this point of the boundary, and again this point of the boundary. So it would be difficult, it would be impossible to create a reliable one-dimensional function or a signature using this method, right? And the reason why is that it would miss all, this region would be missed. This entire region will not be taken into account by the signature. Therefore, one way around that is to consider a reference. For example, say that my reference is this green line, which is a horizontal line. And then what I do at each time or at each iteration is that I consider one, how do I call that? It's a tangent line. I consider at each point a tangent line. So here this is the tangent line. So this point here, this is the tangent line. So I consider at each point of the boundary a tangent line. And then what I do is I measure the angle between this tangent line and this reference line, which is here in green, right? And in this way, I get a signature that represents my entire shape, and this has an advantage over this type of signatures when dealing with some complex shapes like this number 3.